Good evening. How you doing? How's everybody out? It's Coach Scott. Let's talk about polarity. And this is our last little unit in the study of molecules, right? So we've learned a lot about covalent bonds. Okay, we know about electronegativity, and yeah, there we go. Okay, I was lagging just a little bit. We know that in a covalent bond, that one atom is oftentimes more electronegative than the other, but not all the time. All right, we can look at that table of electronegativities and figure it out. So the higher the electronegativity, the bigger the difference, the more that electron will hang out around the higher electronegativity atom. It's going to pull it more because it really likes electrons. And we call these bonds polar bonds because it'll have a positive end, if you would, slightly positive, and then slightly negative, right? Where all the electron likes to hang out. And we call this a dipole. Why do we call it a dipole? Because there's two poles, a positive end and a negative end. Slightly positive, slightly negative, all right? And we symbolize this with this little symbol right here. So, of course, the more positive end would be where the plus is. And where the arrow is showing where the negative end is, right? So, if we've got an identical atom and they've got the same electronegativity, we'll say that bond is nonpolar. It's not going to be attractive to other things. It's not going to, the electrons are going to hang out around both of them because, well, there's nothing in there. So, hey, we got our little changes in the difference in electronegativity. We've got to throw two more at you. So we pretty much use this, that we say that any electronegativity difference above above 1.7, pretty much between a metal and a non-metal, we call that an ionic bond where that electron is totally grabbed by the most electronegative element, the non-metal, and we use 1.7 for that. So we'll say that the bonds are more polar, all right, if we have a electronegativity difference between 0.4 and 1.7, okay, in that domain. Okay, we'll say that it's polar. We'll say that something is non-polar covalent. There's no different little areas if the electronegativity difference is less than 0.4. And again, we've got our chart of electronegativities, and I can print one out or I'll put it on OneNote to where you can use this if you need it to do your calculations. So what do we mean by that? Now, just because a molecule possesses a polar bond, because each of the bonds could be polar, does not necessarily mean that the molecule itself will be polar. Let's look at CO2. Now we see that we have linear geometry. We went over that. And that's a pretty polar bond. And we can see that carbon is more positive, the oxygen is more electronegative. So each of these bonds will, the electrons will hang out around the oxygen. So both ends are negative. So those dipoles, or what we call the dipole moment, will cancel each other out. All right? Because the arrows are the same length, okay, and we add them like vectors. We're going to play physics here, and they'll cancel each other out. So we say that's not a polar molecule. So we almost have to know the shape or understand the shape, draw the Lewis structure, to understand whether you're going to cancel those poles out. So by adding these individual bond dipoles, we can determine what the dipole moment for the molecule is. Now, for the molecule to be polar, it has to contain one or more dipoles, and they have to be arranged around the central atom asymmetrically. Let's look at water. All right. So these are not they're not linear. They've got a bent shape. All right. So you've got a dipole going that way and a dipole going that way. The overall dipole moment goes like that. All right. So molecules with lone pairs for the most part, will be polar. So water, the oxygen side is slightly negative, and the hydrogen side would be slightly positive. Thank God. Okay, that way. Thank Allah. Thank whoever. Because if it wasn't like that, we wouldn't be around. Okay? This has a unique design to it. So let's look at some of these molecules. You got HCl, all right? And you can ask yourself, we'll ask yourself in class, is that polar or nonpolar? Well, of course, it'd be polar because it has a dipole from the hydrogen to the chlorine. Boron trifluoride, well, there's dipoles on those bonds, but they'd cancel each other out, wouldn't they? Nonpolar. Methane, CH4, or actually that's carbon tetrachloride. You've got 4 dipoles, but they would cancel each other out. Now, NH3, ammonia, I think that's going to be, because they've got a lone pair there, that'll probably be polar. And this is methyl chloride. That's asymmetrical. It's going to be polar. And that's where we are. And if you look at those, that's polar, polar, non-polar. They cancel each other out. So you might be able to see a pattern. And you will. Now, why are we worried about polarity? How do we know if there's something that's polar or not? Or what does it do? The polarity affects the melting and boiling points of the compound. Okay, let's look at these. You got hydrogen, you got methane, you got ammonia, SO2, silicon dioxide. You can see, sulfur dioxide. You can see that the boiling point's increasing. Let's think about why. Because the polar molecules are attracted to other polar molecules because it's got a positive and a negative end. All right. It's going to require more energy to pull, all right, by boiling, to pull those molecules apart. That's what we do when we boil something. All right, so we can see that water's pretty polar. And we'll do some of these in class. And our next little section, of course, we'll do all these in class. Let's look at this. Which of these would be polar? Well, B's going, which one would be polar? Let's guess. Water, well, that's pretty much a polar molecule. All the rest of them, let's look at C. Carbon monoxide, yeah, that's going to be polar. The answer for that should be C. And it is. I guess that's why I am the teacher. All these others have polar bonds, but they're canceled out because they're symmetrical. Okay. And again, these will go through class. Cl2, HCl, that's pretty polar. That's non-polar. Carbon tet. Hydrochloric acid, HCl, should have the highest boiling point because it is polar. And it's going to be hard to cancel those out. Okay, so guys, that's everything on polarity. We've covered molecules. We're getting ready to go do some other things. So anyway, this is Coach Scott saying, love you guys and have a great day. Bye.